go wrong? It's got to be able to work. So in theory, we are live, but I need like some human being to tell
I
me.
see it. You're
You actually can see it happening?
yes.
All right. Well, then we've got to assume that this is going to work. Hey, Paul. It's been so long.
It has, hasn't it?
Yeah.
See,
4 hours since we did the
I
weekly
know,
update.
right?
Yeah.
Yeah, we were so young then.
Yeah, exactly. If we knew then what we know now,
Now,
then yeah.
then we would it be honestly the same.
Yeah.
We
Yeah.
haven't changed
Yeah.
much.
Some
The
kind
only
of
difference for me has been dinner.
That's right. You are living in the future though, right? You're living
Indeed,
3 hours into my future.
indeed. It's great. It's darker, but it's closer to bedtime.
Well, we got three people. Apparently, we have three people watching.
Says the thing.
Says the thing. Yeah, so we'll hang out, chat, say hi to some people. Lots of noise.
Ooh, is that me?
I don't think so. Is anyone else hearing lots of noise? Um,
I'll try and mute.
well, are you getting the? You're not getting the audio. No, you're just paused on the actual live stream, or
I muted the live stream.
yeah. Okay, all right. Oh, he says it's gone. Never mind. Hey, Bart. So if you have no idea what it is that you have stumbled into, Paul and I have a new
Neither
episode.
do we.
Neither do we, yeah. So Paul and I have a new episode queued up. The next episode of The Guide to Space. So we're going to be watching. We're going to watch that episode, which is going to take about, I don't know, like 18 minutes, 14 minutes. I forget how long it is. Let me see.
That's a long one.
It's 14 minutes and 13 seconds. So we're going to watch that. And then we're going to stick around because I know you're all going to have a bunch of headaches. And then we're going to answer your questions about what just happened.
What happened?
what,
What happened, man?
what the hell was that? Yeah, that's the plan. And it's a pretty complicated. Oh, John needs to go to the washroom. We'll wait for you, John.
Just
Something
you.
something hitting the mic. Paul's louder. Oh, as usual.
Yeah, sorry about that.
Yeah.
Can I control the gain anywhere?
I could control the gain on my device. I mean, I can do. Let me move my. Let me get.
Oh wait, yeah, I can do the gain back here.
Let me get a little better with my mic control. There.
I turned down my gain, and I'm gonna stick my microphone on a book so that every time I tap, I think when I tap my desk,
Yeah.
you hear.
Yeah.
Let me stick it on a book.
John Mike wants to know if this is live. This is live. We are doing this. We are literally about to.
This is good
This
TV.
is good TV. Yeah, go ahead. It's fun. Tell Carla it's fun. Okay. All right. Have a shower. That's cool. Yeah. So say hi to everybody. If you hear a shower, my daughter's having a shower. Okay. Yeah, it's fine.
It's cool.
It's fine. It's fine. They're so scared. The kids are so scared to make tons of noise upstairs because they sometimes stomp around.
Or they get the switch.
Right. Or we're gonna make them watch this episode.
Oh, that's worse.
Yeah, I know. Yeah. So anyway, we'll stick around. We'll watch the episode. We'll answer your questions, and we'll stick around for an hour. So, we we did this last week with our. I did this last week with the Cassini episode, and that was a lot of fun. So I think if I can get organized and do this on a regular basis, I can try to actually do this. I don't know of any other YouTuber that does this, and I think it's a clever idea. So let's do it.
It's brilliant.
Yeah. Yeah. Well, I mean, it's just to give people that, that advanced opportunity, a little, instead of just watching the video popping in the feed, they can get a little context. So, all right. I think people have had their 5 minutes to show up, sit down. I know a whole bunch of people are going to be popping in later on, but this is how this works. Okay, let me just get the episode queued up. There it is, full screen. There's audio is full. Yeah. Fraser, organized? Yeah. All right. Here we go. Here is the YouTube screen. Let's do it.
See you on the other side.
All right. The concepts you can try to wrap your mind around is the true nature of reality. I mean, when I look around with my meat eyeballs, I see trees and houses, rocks, and a camera. But I know that these things I see aren't actually what they really are. I mean, when we see colors, we're seeing photons of electromagnetic radiation emitted or reflected from the objects around me. The color green that I see, so much green, isn't green at all. It's just photons with a wavelength of 495 to 570 nanometers, jiggling photoreceptors in my eyeballs. I think that's the technical term for it, which my brain uses to construct an idea of the world around me. Am I feeling the ground beneath my feet? No, again, my brain is interpreting signals from nerves that tell me that I'm standing. Since we can't even trust our own senses to know if we're actually in reality or living in a simulation, it's really, really tough to try and decipher the underlying nature of reality itself. But of course, the question, what is the nature of reality, is so fascinating that scientists can't help themselves to try to get to the bottom of it. One theory that I'm sure you've probably heard is the holographic principle, first proposed by Gerard de Hooft a few decades ago. And this theory claims, actually, you know what? This question is way beyond my pay grade. Once again, it's time to call in a bigger brain, Dr. Matt Sutter. Dr. Sutter is an astrophysicist at Ohio State University and mainly studies the largest nothings in the universe, cosmic voids. He also hosts a fascinating podcast called Ask a Spaceman. Hey, Paul.
Hey.
Welcome back to the Guide to Space.
Thanks so much for having me. Virtual Fraser.
We got a tough one for you today. The holographic principle.
Are you ready for a mental beating?
No, but I have. No. We'll do the best that we can to struggle through this. So before we get into the holographic principle, let's lay some groundwork here and just understand what is a hologram.
Good question. So a hologram is very simply, it's a mathematical thing where you encode high dimensional information, like say 3-dimensional information, on a lower dimensional structure. So that's most commonly used in the eponymous holograms, where you're actually storing 3-dimensional information about a structure's extent and properties in a 2-dimensional form. So you're pulling out all the information you need out of the 3-dimensional image and you're storing it in 2 dimensions, and then you can recreate it at will.
Right, and I think the thing that's important for this conversation is this idea that you are encoding a higher dimension of information in a lower dimension and can kind of access it. So how does this lead to the holographic theory of the universe?
Yeah, so it actually starts not with the universe itself, but with black holes. It was found about a couple decades ago that if you were to add 1 bit of information to a black hole, the black hole would grow because that bit represents energy. And so as black holes consume things, they grow. But if you add exactly 1 bit, the surface of the black hole grows by a very specific amount. It actually grows by 1 square Planck unit. So a little square with a Planck unit on one side and a Planck unit on the other. So interesting when it comes to black holes, the information content of a black hole is proportional not to its volume, but to its surface area. And so there's this kind of intuition that the quote unquote information that fell into a black hole, the record of everything that fell into a black hole may not actually be inside of it, but may be kind of pasted on its surface on the event horizon. And that event horizon, that surface, is 2 dimensions. So you're encoding 3-dimensional information about the universe of everything that fell in onto 2 dimensions. Now, going from black holes to the universe isn't quite as challenging as it may seem. There's, again, this intuition or this possible interesting thought. I want to caution that these are very speculative, theoretical physics things happening here.
Right. Possibly untestable.
Possibly completely untestable, even in principle, but we'll get there. We'll get there. That it could be that all the 3-dimensional information of our universe, or 4-dimensional if you include time, if you were to splat it out onto our cosmological horizon, which is the limit of what we can see, that 2-dimensional surface would contain an accurate record of everything that's in the universe, and you could reconstruct everything in the universe if you so wanted to.
But the way that makes it sound, and I think the way it's often described in magazines and online newspapers and crank theories, is that we're living in a hologram? Is that how this... That's what it sounds like.
Yeah, and you know what? You actually can't blame the crank theories for once, because if you go read Gerard Touffe's original papers on this subject, like the title, I forget the title, but it's something like, life in a hologram, or the theoretical physicists themselves are kind of using this kind of flowery language to explore this metaphor. But really what it is, it's a convenient mathematical tool. Because some questions in physics are super hard. Questions like about gravity. And solving it in our full 3 dimensions is really, really hard. But it might be, and again, might be, easier to solve these problems on the 2-dimensional surface rather than the 3-dimensional volume. And so it's not really that the universe is 2-dimensional and we're living in a 3-dimensional projection of it. It's just that there's some convenient mathematical translations that we can take advantage of to make our mathematical lives easier so that we can make predictions about how the universe works.
Okay, so then why does a theory like this exist? I mean, at the heart of it, what are physicists trying to explain with the holographic principle?
Right. The name of the game here is gravity. We do not understand quantum gravity. We have no quantum theory of gravity. And solving that appears super hard in our 3 dimensions. We just have no theories. All of our theories break down. All the mathematics leads to infinity.
Right, that's what I understand. Like if you try to take your equations for quantum mechanics and try to plug in gravity, everything goes to infinity, nothing makes any sense. It's 2 things that just do not go together.
Yep, and so it just goes nuts. But it was found that if you make this mapping, if you make this holographic mapping from our 3-dimensional universe to the 2-dimensional surface, when you perform that operation of making the mathematical translation, gravity disappears. It just goes away.
Well, that's helpful.
Yeah, that's super great, because then you don't have to worry about it. So our 3-dimensional universe with gravity might be equivalent to a 2-dimensional universe with no gravity. And so the hope, and again, this is bleeding edge theoretical physics. There's this, I'm talking about it in super sketchy terms, because that we just have the barest sketch of an idea here, that instead of trying to directly tackle quantum gravity, instead you make this transition to the 2-dimensional surface of the universe, do some calculations there that are normalizable or renormalizable, that don't lead to infinities, and then make the translation back, and you can make predictions of how our universe works.
Okay, so that's starting to make a little bit of sense to me. It reminds me of times when in math, in high school and even in university, where you would take some equations that you're working on, you'd move them to a place to look at them in a way where a lot of the complexities were not there, solve it in a certain way, and then bring it back and reinterpret it to give you a bigger picture. And so it's like, if the physicists can really wrap their heads around it in this two-dimensional way, then it gives us some inkling, a better understanding of what the nature of gravity really is and how we can mesh them back together in terms of quantum mechanics.
Exactly, exactly. But again, the big caveat here is that this mapping between the three-dimensional universe and the two-dimensional surface may not apply in our actual universe. It may just be a mathematical fiction.
Right.
On that two-dimensional surface, we don't exactly have robust mathematical models or descriptions of what's going on, and then going from there back to predictions of the real universe or our three-dimensional universe, those connections are super tough and super fuzzy. So there's like three potential ways that all of this could break down.
All right, well, in a second, we're going to bring it around and explain why the holographic principle was in the news all over again. But first, I'd like to thank Steve Wolfhope, Matt Douglas, Tom Van Scotter, Jeff Borst, Viva Tomlin, and the rest of our 698 patrons for their generous support. If you love what we're doing and you want to help out, head over to patreon.com/universetoday. So, as I mentioned, in the news recently was a new announcement that the holographic principle has more evidence. What was going on here?
Yeah, so like I said, these connections where you map from the three-dimensional universe to the two-dimensional surface, you do some math with no gravity, and then you turn it back around to make predictions of how the universe works. That's all super sketchy, but theorists are starting to make some inroads, and they're starting to make some predictions of how the early universe ought to behave. And we can't directly probe like the first second of the universe in the Big Bang, but we can study the afterglow light pattern, that cosmic microwave background, which was released just 300,000 years into the Big Bang. So we can make predictions of the very early universe, and we can see how that might play out 300,000 years later when the cosmic microwave background was released. And so already there are some, again, very sketchy, vague theories, but some of them have already been ruled out by observations. And there's a few intriguing paths that I don't want to say confirmed by observations, but they're allowed by the current levels of uncertainty in the observation, and they don't necessarily do any better or worse than any other existing model that doesn't include all these projections and deep projections into different dimensions.
Okay, so it's kind of like I know when you're doing science, when you're sciencing, you are trying to essentially invalidate your own theories. You're looking for reasons why your theory isn't going to work. And if I understand, then new discoveries, new models for the universe don't invalidate this holographic principle, so it's not dead yet.
Yeah, and that's because the holographic principle is really just that. It's like a statement. It's a very broad and general statement. What really matters is the mathematical guts. And we haven't fully fleshed out those guts yet, but there are some intriguing sketches that some of those sketches have been ruled out by the data and some haven't.
All right. Well, that's it. Thanks a lot, Paul.
Hey, no problem.
So if we've done our job, you have a better sense of the holographic principle and what it means to help us understand the universe around us. Thanks again to Dr. Matt Sutter for helping me, even if I'm already confused again. This topic was requested many times. See, we listen. What other baffling concepts in space and astronomy would you like to learn about? Let me know your ideas in the comments. And make sure you go to Dr. Matt Sutter's YouTube channel, Ask a Spaceman. We'll link it up right here. All the large planets in the solar system have rings, but Earth doesn't have rings. What's that about? Why doesn't Earth have rings? What would it look like if it did have rings? Is there any situation that could give us rings? That's coming up in our next episode. One related concept of the holographic principle is the black hole information paradox. If you want to understand this bizarre concept, which actually Paul helped to understand even a little better today, here's a video that'll help you out. Gave me a headache making it, so I hope you enjoy it. Boom! We made it. We survived.
Everyone's still here.
Maybe? Or maybe
Did you take a head count?
After the savage head beating. Cool. Well, thanks, Paul. That was super fun.
Oh, thanks so much for asking me. It is a really fun and interesting topic.
Yeah. So a couple of questions that people were wondering whether that was my garden or whether that's a park. Sometimes we shoot in my garden and sometimes we shoot in the park. So we are surrounded by forests in all directions, and we have dozens. We've shot in dozens of different parks in the area. In fact, we're really choosy at this point. So we want a place that doesn't have a lot of noise, that we can get to with a car, that we can kind of park and pull out all our gear and set up in the forest, that we can find a place that isn't going to be near trails, that's got the right sort of blocking of the light, but not too dark. So, and it doesn't look, and depending on the time of year, you know, what we want in the background. So at this point, we're pretty picky and choosy about where we shoot. But the cool thing about it is that when we do that, then it's way easier than us shooting inside it all, right? Like we shoot and the lighting is sort of almost perfect, and then we just, you know, we light it up a little bit more and it's great. So yeah. So but if we're like, we just gotta get done right now, we gotta then if you see the cedars in the background, then you know that episode was shot in my backyard. And then in the summertime, we've got, like, you know, my wife is a macro photographer, so we have flowers everywhere and looking for bugs, and so we have like sunflowers and things like that we shoot outside. But yeah, pretty close. Like, it takes us about 5 minutes. Right. But the funny thing is that people, like, it takes us 5 minutes to get where we shoot. But, you know, and then wildlife sometimes shows up. So we've had deer walk through an episode. We've seen bear walking home, and we've had eagles show up and chirp in the middle of the episode. And yesterday we had ravens show up, and they were like in the tree right above us, and they make this really distinctive noise. So that, I hope that answers that question. So some people were asking about black holes merging, and you were mentioning sort of briefly in the chat, you know, can you get two black holes, you know, as two black holes come together, and I guess they sort of overlap their event horizons?
Yeah, exactly.
Yeah, what's going on?
The event, when black holes merge, the event horizons kind of stick together, they touch each other and then envelop. And then actually, because of the rotation that's happening as they're orbiting closer and closer to each other, after they've merged, there's almost like what we call a ring down period where the event horizon is almost vibrating as the singularities actually coalesce in their centers. And this is exactly what LIGO detected with gravitational waves, is the waves produced by the merging black holes and then that vibrating of the final merged object. So yeah, you can have multiple singularities co-located within the same event horizon for a very brief amount of time.
But would you, like, actually be able to tell the moment when the singularities come together within that shared event horizon, or are you, like, is it too kind of messy to know?
I think there's a point where you could say where we don't fully understand what's going on in a singularity. And so you can definitely say when the singularities are close enough that you might as well act like they're a single singularity rather than two separate objects, regardless of what is actually happening down there.
Yeah. Let's see. So Arjun is asking, how can black holes merge in the lifetime of the universe? What about time dilation? And I think I understand what they're getting at, which is that, you know, because of the time dilation, we saw this in the movie Interstellar, that the time you experience near a black hole is vastly different than the time you experience far away. And if we watch objects fall into a black hole, we're going to see them slow down, time dilated, redshift, pause on the
Mhm.
on the event horizon. How do we know? Like, are they actually merging?
Yeah, so this question gets at a few topics in general relativity. Yes, different observers can disagree about the pacing of events. So if you were to fall into a black hole, you would just fall into a black hole. You wouldn't even notice the event horizon. But a distant observer would watch you just almost get stuck, not quite stuck, but slowly approach the black hole and get ever more redshifted and ever more slowed down. And we understand that because when we look at the equations that describe a black hole is a certain solution to Einstein's field equations where there's an incredibly dense mass with a static background. Two black holes merging is a different problem. It's a different set of mathematics. It's a different solution to Einstein's field equations. So we can be out here in the universe or outside of a black hole. And regardless about the behavior of objects approaching event horizons, we can define the event horizon of a black hole and see how that warps and bends and potentially merges with another black hole, regardless of what an observer near the boundary would experience, and regardless of what we think would happen if you were to approach a single stationary black hole. Two black holes merging, we know we can predict exactly what this looks like through general relativity, and that matches the observations we have from things like LIGO.
Right on. But would the merging black hole fall under the information paradox? I mean, a black hole has already mangled the information that's falling into it. If you then take it and run it through a second mangling, does that cause a problem?
Yeah, I don't think it causes any more of a problem than the original information paradox of black holes. Just the information content. If you have two black holes, the information content is summed when they merge. And so that means the surface area of the combined black hole is doubled to accommodate all that information.
So Phoenix J55, can wormholes be a plausible phenomenon? What do you think?
Nope.
You're against it?
I'm not against it. Physics is against it.
Yeah.
It's not me, man. It's not like I get
it. Yeah. Yeah. You'd like to walk through a Stargate as much as anybody, but
yeah. So black holes are, like I said, a solution to the very complex equations of general relativity. Wormholes are another solution to the equations of general relativity. Just because they're a solution to the equations of general relativity doesn't mean they actually manifest in our physical universe. You can have solutions to math equations that make no sense based on other physical considerations. And when it comes to wormholes, when you go to solve the field equations, the Einstein field equations, to make a little tunnel with a tube or a throat or whatever that you can travel through in finite time and all the things that you want a wormhole to do, you find that in order to structurally support that deformation of space-time, you need materials with a very peculiar property. You need materials with negative mass, like negative 10 kilograms.
And we're not talking about antimatter, which has regular mass. We're talking
antimatter is regular mass, but different charges. Negative mass really does mean mass that is negative, and that's just not a thing in our universe. So we don't get negative mass things, ergo we do not get wormholes.
So figure out how to make some negative mass, and then we can talk about
step
one, negative mass.
Step two.
And if you got negative mass, then you can do all kinds of other things. You could have some anti-gravity. You could have...
if you have negative mass, you basically break everything. Because positive mass charges attract, negative mass charges repel. And so you can have like a positive mass and a negative mass particle sitting right next to each other, and they'll just accelerate themselves off like a freight train with no external forces. And that seems to be like a wrong thing to do. We just don't observe it in our universe. And so there's all sorts of violations of, say, momentum that you could get if you had negative mass.
But it would let us live our science fiction dreams.
You know what? If you're going to have, you don't need negative mass to live your science fiction dreams. If you had the energy to put together a wormhole, if you were to accumulate all the stuff you need to make a wormhole, it's better to just make a rocket and a really, really big rocket. And people don't pay attention to this part of special relativity, which is if you go really, really fast, like if you really push the speed of light, and you left Earth and headed towards the center of the Milky Way galaxy, yes, someone on Earth would see you rocket off towards the center of the Milky Way galaxy, and it would take you like 20 or 30,000 years to reach the center. But you, because your clock is running slower on that super fast spaceship, you can reach there in like a decade.
Mm-hmm.
A decade of travel, you can go across the Milky Way galaxy if you're going fast enough.
I did the math one time, and you could actually get out to what is now the observable universe within your lifetime. So you could get, a distance, you get out like say 14 billion, 13.8 billion light years away within your human lifetime. You'd be pretty old.
Yeah, if you're accelerating at like a constant 1G or 2 or something like that.
Yeah, exactly.
Moving clocks run slow, and you can use that to your advantage.
Yeah. But everyone you've ever known and loved has been dead and gone for
that's not necessarily a negative.
Right, of course. So Arjun is also asking, have they solved the quantum gravity problem in the holographic principle universe, the 2D universe without gravity?
Yeah, so this whole discussion about the holographic universe, which is neither holographic nor universal, but it's just a jargon term, is a possible, maybe, kind of, sort of route to perhaps getting a handle on one day solving quantum gravity. Maybe.
Right.
Have I put enough hedges in there?
I think you really did. You hedged it pretty hard there, yeah.
Because it's all super sketchy. It's all super sketchy because we're not exactly sure what we're doing. We're not exactly sure where the math leads. The math isn't very strong or very informative at this stage, but it is one route that, hey, it turns out that gravity we don't need to solve gravity in a quantum way because really we can look at the universe in a two-dimensional way. And in that two-dimensional structure, there's no gravity at all. And we can solve all our math problems there, and we can make predictions for the rest of the universe. Right. Or the real universe.
Yeah. So once again, that's Dr. Paul Matt Sutter. He is an astrophysicist and helped me do the episode that we did at the beginning of this show. If you've got some questions for him or me, then just post them in the chat.
Talking about your garden.
We can talk more about my garden if you want.
That's cool too.
Yeah. Let's see. Whoa. Sean Leonard asks if superfluid helium simulation support the holographic universe. I don't even know what superfluid helium simulation is.
I don't know. I know what superfluid helium is. I don't know what simulations there are of it.
Man. So Seaman is asking, would you go if you could never see your friends and family again, other humans in this life? Would you be willing to spend your lifetime exploring the universe if that meant that you had to time dilate out everything else?
I don't know, because our telescopes are pretty good, and a quasar up close doesn't look much different from a quasar from far away. In fact, it's probably preferable to view it from far away because you would be annihilated and dissolved and irradiated. So, some things in the universe are better left being on the opposite side of the universe. It's kind of nice down here on Earth.
It is. And I think that, this is one of the questions that I often get from people. They're like, would you go to Mars? Once people are colonizing Mars, would I go? No, I wouldn't. Right?
It's cold.
It's cold. Red. There's no air. Nothing grows. Like it's a terrible place.
You can jump higher there.
You can jump higher, right? And it's a terrible place.
It's not friendly.
No, no. Earth is better. Like if you're in any way intrigued by the desolate wasteland of Mars, go to Antarctica and and just
And after 15 minutes, you're like, oh,
oh,
okay.
right, of course. This
I get it
sucks.
now.
Yeah, yeah, right. I want pizza. Right.
I want pizza.
This is terrible. I want to go home. I want to be warm for 1 second and like be able to walk outside and not be concerned about the amount of radiation. The people who are willing to go to Mars are, I mean, they're doing this despite of how much it's going to suck, and they're doing it because they want to push humanity out to the next point, and I applaud them wholeheartedly. I mean, I think that's a wonderful and noble gesture, and Godspeed.
Yeah. I would say if you're going to pick anywhere in the solar system, pick somewhere with a better view, like one of the moons of Jupiter or Saturn, where at least if you go outside in your spacesuit, you can look up and enjoy like a really beautiful, ever-changing vista.
Yeah.
Mars is just going to be
right.
red.
And then the counter to that, right, is that if you could go to Mars, if you could hop on a spacecraft and spend, say, a few months traveling to Mars, pop down on Mars, go to the Martian hotel, spend a couple of weeks on Mars, and then come back home. Now we're talking. Oh, that would be okay. I'd visit.
Vacation on Mars.
Yeah, vacation on Mars. Vacation in orbit. So that's sort of my feeling.
I saw Total Recall. It seemed like a good idea.
Physics Police wants to know if you've read Lawrence Krauss's book yet.
Nope.
Nope, but we're going to have him on the show in a couple of weeks. So I actually have interviewed Krauss like 8 years ago. So if you search my name and his name, you can hear an interview that I did with him. But he'll be coming back, which would be great.
Who is Dr. Paul Sutter? It's me.
Yeah. Can you give us any more information?
Let me see. I got my PhD in physics from the University of Illinois in 2011. I spent 3 years at the Paris Institute of Astrophysics in France, or the Institut d'Astrophysique de Paris, as a research fellow there, and then 2 years at the Astronomical Observatory in Trieste, Italy. And then back in the States, I'm split between Ohio State University as an astrophysicist there and also the chief scientist of COSI Science Center. So I get to do research, I get to do teaching, I get to do outreach, I get to have lots of fun.
Is that like what Neil deGrasse Tyson is to the planetarium in New York?
Yeah, so he's the director of the Hayden Planetarium, right, which is a part of the American Museum of Natural History. COSI has a planetarium. Obviously, COSI is a much smaller institution than the American Museum of Natural History, and so I'm the chief scientist for the whole organization here.
Yeah. So you have to deal with other kinds of science than just astronomy.
Yes, and when it gets too far out of my field, I'm trained as a physicist, as an astronomer. When it gets too far outside my field, I bring in other experts from OSU to help consult, help look at scripts, help develop programs, help show up for special events and things like that.
Right. Scott W., how does the expansion of the universe fit into the hologram theory? Oh, hold on. Does it imply information being added to our universe like a black hole surface, growing more information?
Yeah, that's actually a really, really good question that cuts deep into these discussions. When I say that the holographic models of the universe are super sketchy, this is one of the ways in which it's super sketchy. The mathematics, to make the mathematics tractable, to make them actually solvable so you can make headway, you have to make certain assumptions, just simplifying assumptions that get rid of lots of terms and just makes your life easier so you can get somewhere. A lot of those assumptions assume for the moment that the universe is static. They haven't actually incorporated an actually dynamic, expanding universe into the work to determine what the consequences of that are. And also the relationship between the two-dimensional surface and the three-dimensional universe assumes that the universe has a certain energy content. It actually assumes that the universe has what's called positive spatial curvature. And it's under that framework that the mathematical connections between the 2D and the 3D things become feasible and tractable, and you can make progress. But our universe does not have positive spatial curvature. It actually has negative spatial curvature because of dark energy. And the implications of that haven't been worked out. That's why a lot of this is just so super sketchy, because there aren't a lot of connections between these models and the actual universe.
Right. As if that matters.
Yeah.
Yeah. Yeah.
Never stopped a mathematician before.
No, it really hasn't. So, okay. So Ernie Jacobs wants to know, why does the Drake equation use the rate of star formation instead of the number of stars? What do you think about that?
Yeah, so the Drake equation, if you really want to call it an equation and not an identity, there's a bunch of problems with the Drake equation. And I guess the reason that they use star formation rate instead of number of stars is if you're looking at, say, human timescales, like over the course of a human lifetime, what are the chances of encountering or hearing or finding terrestrial life? And just the number of stars isn't going to tell you the likelihood of encountering extraterrestrial life, because you need to know the rate that new stars are formed, because that informs how many chances life will have to get started. So if you're popping out 10 new stars every year in a galaxy, then that means there's potentially 10 new chances for them to host a planet, and 10 new chances for those planets to host water, blah, blah, all the way down onto life. But if you just know the total number of stars, then the per year potential detection rate, you're not going to get, say, the right units for that calculation. You need like a per year calculation. So every year that I operate SETI, what are the chances of encountering life?
Right, and earlier on in the history of the Milky Way, stars were forming more often, and into the far future, stars are forming less often. And so the average number of stars that are in the right zone changes over time, and it is an important part of the calculation. And it's probably something that you can bank on better than trying to count up the total number of stars. You can make a better estimate of the number of stars that are forming based on the amounts of hydrogen and such.
Exactly.
Yeah.
And so,
but as you said, right, it is like so much of the equation is uncalculatable to our current state of technology and our sample size of one. So
if you break down the Drake equation, like, I get the point of it, where it's like, okay, let's organize our thinking a little bit better about what does it mean for life to arise. But it's not exactly informative, because even if you took all those factors, like the dozen factors or 9 factors or however you formulate it, even if you're able to pin those down with incredible certainty, that still wouldn't tell you about the likelihood of encountering alien life, because if you left something out, if you forgot an important part of the recipe for generating life, then the uncertainty in that part, that quantity that you left out, would totally dominate all the stuff that you were able to figure out. And it turns out that the number you calculate, actually doesn't tell you anything about the universe.
Right. And so as you said, you could very well realize that, in fact, one of the factors is whether it has a large moon, and whether that moon is a certain distance that helps create tides. I mean, there's certain things that people think are additional ones. I've seen people attempt more modern versions of the Drake equation based on our current understanding of astronomy and geology and the history of life on Earth. So Let's see.
So it's not as useful as like a predictive tool.
Yeah.
It's just a way to kind of help organize thinking when it comes to extraterrestrial life.
Yeah. Susan Hunter notes that some say that life existed 300 million years after Earth solidified, that life has been here for a very, very, very long time.
Yeah, there were these recent microfossils found in Quebec, Canada, potential microfossils. So these tiny, tiny little iron rich tubes that the researchers claimed were a byproduct of single celled organisms in hydrothermal vents for up to 4.2 billion years ago. And then other researchers saying no, there are chemical and geological processes that can lead to very similar looking tubes. Mm-hmm. So it's not 100% certain, but yeah, and there was some news about a year ago about equally old life that ended up being just a chemical process. So right now, we know for sure that life was here about 3.7 billion years ago. I think that's the number. But there, some evidence might crop up that it's even hundreds of millions of years older.
Yeah.
And if that's confirmed, then that's pretty mind-blowing. That basically, as soon as the Earth settled down a little bit, boom, life was off to the races.
Sooner than life could have formed, it did.
Mm-hmm.
Right. And actually, so Seaman is asking, what do we think about fossils on Mars? Do you think that we're going to find microbial fossils on Mars? And what do we think the likelihood of complex fauna is? So, I mean, do you think that, this is still just a guess. Do you think they're going to find life on Mars?
Life today, most likely not. You can't quite rule it out because life can exist in some pretty crazy places, but Mars has been hostile to organics for like 3 billion years. And there are niches in Earth, like the upper atmosphere, deep within ice crust, hydrothermal vents, where life can survive and even thrive. We don't know how long it takes to establish life and to establish the nutrient chains and chemical chains and have the necessary quote unquote support structures so that life can sustain itself. If you were to eliminate all other life on Earth, would the hydrothermal colonies still survive? Will the aerosolized bacteria in the upper atmosphere still survive? Probably, but for how long? We don't know. So maybe microfossils and these, especially what we're learning about when it comes to early life on Earth and finding these little pieces of evidence, that's exactly what we'll be looking for on Mars. We'll be looking for little tubes like this, little evidence for excretions from single-celled organisms.
Yeah.
Finding life today, finding multicellular life is probably not likely.
But the tantalizing piece of evidence, of course, is that they've discovered methane in the atmosphere of Mars, and this is sort of the whole purpose that NASA's MAVEN spacecraft is there right now. The question is it life-based, methanogen bacteria, or is it some kind of volcanic process that is creating the material, the methane in the atmosphere? But some process is creating methane. So we could be very, very just months away from getting an answer on that front.
Yeah, everything I said could be totally wrong.
Yeah, well,
that's science.
Yeah. But sort of the interesting thing about that is that even if you do discover that that there is life on Mars, and even if you find it on Europa, you find it on Enceladus, find it all the way across the solar system, floating around in the upper atmosphere of Venus, who knows, that it could all be related, that still doesn't get you to the answer of whether there's life anywhere else, even if we do find it here in the solar system.
Right. Until we hear the song of the space whales of Europa.
Yeah. Well, and we know that we're not related to them.
Yes.
Yeah.
There's that too.
Yeah. So Jared Mueller is asking, what are your thoughts on the focal mission to use the sun's gravity as a massive telescope lens?
Sounds cool. I actually don't know a lot about
No,
focal.
neither do I.
Mhm.
No. But would it work?
I mean, we see the gravitational lensing of starlight around the sun. The sun isn't that massive when it comes to gravitational lensing. It's very, very small deflections. So you're searching right now, and you can tell me more about focal.
Yeah. I got an article from Centauri Dreams, pretty old. Yeah, I suspect it sort of disappeared. I remember, and I wonder if anybody can tell me where I saw this, but I remember there was like an old book from Isaac Asimov where he was talking about how you could create like a really big interferometer where you'd put like one telescope on one side of the solar system and put another telescope on the other side of the solar system, and maybe a few in between, and then you could combine the light from them and get a really and I always forget the two terminologies, right? You can there's your resolution and there's your sort of light gathering amount.
Right? With interferometers, you get a lot of resolution,
Right,
but
not so
not
much
a lot of aperture.
of aperture. Yeah, and so you could do things like read a newspaper on Alpha Centauri. That if you you could get that kind of resolution, but not. It would be very, very dim, so you wouldn't really be able to see it. But you could get that kind of resolution.
It would be very dim, and so interferometers actually don't act in kind of image space, like so it's not like they pick up little pieces of images. They actually pick up little bits of information in what we call Fourier space. So they pick up modes, they pick up wavelengths of light, and you actually have to reconstruct images from that. So you could get very detailed bits of information about, say, spectra and things like that at very high resolution, but trying to make a picture from that is actually very, very challenging.
Yeah. Let's see. So John Mike is asking, does the solar system move slightly every year like the continents on Earth?
Yeah, our solar system's barreling around the center of the galaxy at 200 kilometers per second, 200 or 300 kilometers, somewhere around there.
Yeah, it takes 225 million years to make one orbit around the center of the galaxy.
Yep, and we're like 20,000 light years out from the center, plus or minus. We're going pretty fast. I mean, slow compared to the speed of light, but the solar system itself is moving pretty fast. We can actually see our solar wind, this stream of particles coming out from the sun. This is what the Voyager probes are actually probing right now, is that kind of bow shock where our solar wind, our stream of particles, is interacting with the general galactic milieu of streams of high energy particles, of that interaction from our movement through the galaxy.
Yeah. Capital H is asking, when we hear about galaxies merging, we hear the stars don't collide and largely go undisturbed. That sounds ominous. Do some merge? How violent would those encounters be? So if you've got two galaxies, like say when Andromeda and the Milky Way come together, how much are we going to get any collisions between stars?
That is a great question, and you guys should tune in to an upcoming episode of Ask a Spaceman. Look at that.
What happens when
galaxies collide?
Can you give us a spoiler?
Essentially, no stars collide.
None.
I mean, yes, some do, but compared to the hundreds of millions or trillions of stars, basically none do.
Two angry bees,
swarms of bees
passing each other. But they're like a kilometer apart from each other as they go by.
Yes, so they do interact gravitationally. So solar systems tend to get disrupted because you'll have lots of stars and clouds of gas and dust kind of whizzing by, and it can disturb the orbits of even inner planets. So it can definitely screw things up. and there will be mergers. So some stars, they won't smack into each other, but they'll swing by each other and then end up getting captured by each other, and then form a binary, and the binary might coalesce to
Right.
make a merge. Yeah.
Very cool. John Victor is asking how we film these interactive videos. So
Magic.
right. I actually left my headphones on. So when we do when I interview Paul for the Guide to Space, I actually call him on the telephone. And so I've got my headphone on, and he's got his headphone on from his, and then I record my side of the conversation, he records his side of the conversation, and then he uploads his half of it into Dropbox, and then we bring it into our video, and Chad makes all the magic happen. So that's how we do it. And we originally tried, if you go back, I think we've done now what? This is like the third one that we've done.
I think the third one.
Yeah, I think the first one that we did was I've sort of prepared all the questions in advance, and then you answered them, and that worked okay. But it was really hard for me to sort of ask follow-up questions, and especially because the topic, we're dealing with virtual particles, and it was very complicated and a lot of like wibbly wobbly, right?
A lot of wibbly wobbly happened in that.
Yeah. And so we, for the next episode, for the next two versions of this, we just had the conversation live. So when you see us talking, we are actually talking, which is way easier, and that way
it works a lot better.
Yeah, I can kind of wrangle Paul as he goes, into wibbly wobbly land, and at the same time,
as I start writing on the chalkboard, then.
Yeah, and he can make sure that I'm actually understanding what it is that he's talking about, so it works very well. Brian Cordova asks, when will we realize man's ancient goal of destroying the moon?
Working on it.
Yeah. We did an episode on this and in the Guide to Space. So if you search, essentially I calculate the gravitational binding energy of the moon, and then try to figure out what sort of ways we could try to actually destroy the moon, or at least carve letters into the moon. One thing that's pretty funny is, like, back in the atomic age, this was one of the things that they were thinking about, was to detonate nuclear bombs on the moon, just to demonstrate the power of it.
I can dig it.
Yeah. Peter Yannick, when are we going to see the first photos from Webb? I need to put it in my calendar.
I don't know. It's an infrared telescope, so it's not going to make pretty pictures.
Yes, it will. They'll just take a couple of filters, and then they'll false color it, and it's going to look fantastic.
So like normal.
Yeah. What's different about that, right? I mean,
yeah, good point.
We do that with, the Hubble Space Telescope. I mean, the funny thing is that the images that come from the Hubble Space Telescope are like, how pretty they look is inversely proportional to how useful they are to scientists. So, the better that picture looks, the less useful it was to a scientist. And if the pictures, you can barely even tell what's going on, scientists are super excited about what they're seeing and the data they're gathering in there.
Show me the spectrum. The spectrum is the most beautiful part.
Yeah. I one time I thought I was gonna get the jump on other journalists, and so I was going to go right into the Hubble Space Telescope raw feed and just see what pictures people are taking, and then see if I can dig back and get some scoops. And I was just like, this is terrible. I don't want to see this anymore. This is boring. But there's some great people who do dig through the Hubble archive, because when you see these really beautiful pictures from the Hubble Space Telescope, it's just a fraction of the pictures that are being released. There's actually a ton more that are in there, and people dig through them, find them, pull them out, process them on the computer. You can make them a red, green, blue photograph, and some of them look really great. El Torture asks, when are we going to mine other solar bodies when Earth's resources come in too much demand for it to replenish? When do we do space mining?
When we can afford it.
But it should pay for itself, shouldn't it? If you go mine that solid gold asteroid, you should be able to make some sweet money from that.
Yeah, you should. I think because it would be really, really expensive to send stuff. Like if you were just having a plan, I'm going to build a $1 trillion rocket, then I'm going to go to the $1 trillion gold asteroid, bring it back down to Earth slowly,
Slowly,
and
carefully.
then sell all the gold. Like, of course, you would crash the gold market right away. But with all that really cheap gold, lots of people would think of all sorts of clever uses for gold that we don't use right now because gold is somewhat expensive. So it would recover. And so you probably would recoup your investment, but it might take like 100 years.
Right. I think the better purpose of that is to keep that stuff out in space. Like you get a rocket, get a factory, get it up into space, stay up in space, mine that stuff up there where you need it, start building space mirrors for power, build factories, and just
giant space statues made of gold,
right. Yeah.
just
Yeah.
whatever.
Yeah.
But yeah, no, it's the most, once you're in space, that's the most expensive part is getting out of Earth's gravity.
Yeah.
There's no reason to bring it back down that gravity well. Just keep it up there.
Yeah.
You'll have a better reason to use it up in space than bringing it back down to Earth.
Yeah, absolutely. Well, we're reached the end of our hour. I hope everybody enjoyed that. Thanks again, Paul, for doing the episode with me. I'm going to make it publicly live now, so you can watch it again should you wish to. And where can people find out more?
They can follow me on Twitter and Facebook. My handles there are at Paul Matt Sutter.
There you are. I put your Twitter handle
up. Very cool. There I am. I also have my YouTube channel, which is youtube.com/Paul Matt Sutter, same name. My website, pmsutter.com, has links to everything I do, including my podcast, Ask a Spaceman.
Right on. Well, thanks as always, Paul. Thanks everyone for watching this live with us. That was a lot of fun. And the episode's going to go live momentarily.
And you need to go to Iceland with us.
Yeah.
There's only like a dozen seats left.
Oh, is that it? Well, we've got an advertisement for it showing up in the feed in a couple of days. So
perfect.
I suspect we'll get rid of them all. So, yeah, right on. All right. Thanks everyone for watching, and we'll see you all next time.